Good morning, all. We'll start the session in next 1 minute. The session for today is on the applications of parametric modeling, its applications in the domain of structural engineering for RCC and steel structures would be taken by Mr. Rameshwar Prasad. So I thank him for agreeing to take this session, and his expertise in this domain he will share with us. That is applicable in modeling for quick and effective applications that you will see through his how he guides us in this session. And you can put your queries. So many have asked that do we have a course after this session? So we will update you later on that. And Mr. Rameshwar Prasad is the founder of Tectum Mechanics. He's from Australia, basically an Indian, but right now he's in Australia. So, Mr. Prasad, I would request you to give some introduction of yourself and proceed with session.
Okay. Thank you, Bhushan. First of all, can you hear me well?
Yeah, you are audible.
Okay, good. Okay, so before we start, just a brief introduction about myself. I'm a structural engineer by profession and have a, kind of more than a decade of experience in the same field. Started off in the nuclear field, then shifted to heavy industrial, petrochemical industries, and then have been involved in the building industry for the last couple of years. And there has been kind of a encouraged use of parametric design for building structures. And that led me to wonder, why can't we use the same philosophy for industrial? And that's how basically data mechanics came into existence, that we could use the same tools that we use that are generally used by architects or even structural engineers from the building industry or from the bridge industry. We try to adopt the same tools and come up with some integrated digital workflows to reduce the design time. So yeah, currently I'm based out of Brisbane, Australia, and we've been here for the past 3-4 years, I would say. Okay, so without much ado, let's start. So today's topic is computational design. You must have heard the term computational design, parametric design, algorithmic design, generative design a lot of times, and I must have always wondered what all these terms mean. So first, I'll try to um, what do you say, expand upon these topics slightly, and then I will slowly divert it more towards parametric design, trying to explain or trying to put forward why parametric design is much more appropriate for real life structures, especially from a structural engineering perspective. So hope all of you can see the screen.
So I'll just have a quick check on all. All are able to see the screen and all are able to hear, right? So anybody can just speak up on that. Sharad, Rinan, is it audible to you and visible to you?
Yes. It's visible, audible.
Okay. Yes, we can continue.
Okay, so the first question: what is computational design? So essentially it is the use of algorithms and parameters to digitize your modeling process, your analysis process, or even your design process. Now, when from a design perspective, so when I talk about design over, it is not just structural design, but when you ask an architect or an industrial designer, who does a degree in MDes, so what he will say is basically what they more or less lead to is essentially modeling, right, and the stability of the model from various perspectives. So essentially, we use a set of algorithms and variable parameters to define our problem, and that encompasses computational design. Okay, it is all you. In other terms, I read this somewhere on the internet, which I found quite apt, which is called the derivative of the combination of human design techniques with the computer that results in enhanced permutations and combinations. So, what the author was essentially trying to say is that if you try to manually come up with alternatives for a particular arrangement of a structure, you might be able to come up with 3 arrangements, 4 arrangements, or the max 10 arrangements because of various deadlines, right? So computational design enables you to surpass these limitations and gives you multiple solutions that obey certain conditions. And that's where you will see that it has a high amount of application. Now, what's the difference between CD versus CAD? So CD, when I say CD, it is basically computational design and computer-aided design. So if you remember the era of 70s and 80s or even early 90s, people, not early 90s, I would say, but at least 70s and 80s in mid-tier engineering firms, at least, people used to do manual calculations on a piece of paper, then draw the GA, general arrangement drawings, the reinforcement details and everything on big drawing sheets, and then and the contractor used to take them up and then construct, right? Then the process slowly shifted to a PC where you started modeling in software like StatPro, initially DOS-based, and then using a mouse and a keyboard. Then you started drawing in AutoCAD and basically essentially digitizing that process. But there was no core logic involved. So whatever you put in, the computer did exactly that. So that is computer-aided design. Okay. While computational design, what happens is you put in a certain amount of logic so that the computer is able to think by itself and judge by itself. That enables the computer to come up with uh, a plethora of solutions. Okay? Now, so if you say CAD, what is it? It is basically human intervention plus a PC, a hardware, and a software that enables the human mind to whatever idea has been conceived in the human mind to put it into to give it a digital life. Okay. Whereas computational design definitely has a certain amount of human intervention. It also needs hardware and software, but it also needs a certain rules, a workflow, a certain kind of what do you say, rules-based system that enables the hardware and software to judge whether the design is appropriate or not for the given conditions by the human. Okay, so types of computational design. Obviously, you first have the main set that is called computational design, and what are the subsets or what are the different types of computational design? So first is the parametric, where you have design variables and rules that control the design model. The second is generative, where the user-defined inputs produce quite a few design solutions, and then you select a particular design solution based on your requirement. Okay. Algorithms, you set in, you put in a decent amount of rules using algebra, and the whatever solution is obtained from that algebra, that is used to create structure. And I'll show a very interesting case study for that one. So parametric design. So parametric design is essentially a tool that helps you parameterize structures. So what I mean by parameterization is, say for example, if you have a steel platform which is 6 meters long and 6 meters wide. So let's say 12 meters long, 6 meters wide, and you have 3 bends, right? Now, if tomorrow if the client comes and says, hey, can you make the spacing as 6.4 and then increase the total length to 12.8? So if you were doing it manually in a software like StatPro or in Tekla, what you have to do was, move the elements manually using a mouse and a control, what do you say, the mouse, the move command in StatPro, or in Tekla, if it were your model using magnetic grids, then change the grid spacing, right? So attaching a dynamic value, that means a value that can be changed during runtime, makes it easy for incorporating those changes. And that is what parametric design is all about. Now, generative design. Generative design, how it varies with respect to parametric design is, you given a certain amount of limitations to a particular case, and then the computer comes up with a lot of solutions that basically follow the limitations or adhere to the limitations. What I mean by that is, for example, if you have a plot of land and you want to come up with an arrangement where you want to provide a parking lot. Now, if you want to do those things manually, The only limitation is that the parking lot should not exceed the boundary of the land, and if there were multiple levels, then they should not exceed the building envelope. Right now, the as you can imagine that the limitations are few, but the combinations and options can be many. So that's where generative design kicks in, that you put in certain boundary conditions and then it comes up with multiple solutions and you decide which solution which is appropriate for you. Because of its power and its limitations, power by the sense, because of its ability to provide multiple solutions in a short time frame. But again, it's because of its inability to adhere to multiple boundary conditions. You will see a wide application in greenfield architectural projects as well as manufacturing, where you want to manufacture, say, a bracket, which is shown on the right over here, bottom right, or even the bike frame that you can see on the left. So where the boundary conditions are limited and you can precisely define the loads, that's where generative design comes in. Algorithmic design. So algorithmic design, more or less, if you'll see, um, it is generally used by architects and even by structural engineers, but where the architecture and structural engineer go hand in hand, and there are few limitations as to what do you say, uh, uh, there are few limitations that the structural engineering is subjected to, unlike typical architectural buildings. So where you have these free-flowing shells or free-flowing uh, roof type structures, which are very aesthetically pleasing and so on. So that's where you will see algorithmic modeling. One of the examples that I have given over here is the modeling of a staircase with respect to the Fibonacci series. So Fibonacci series is basically a sequence of numbers, and then those numbers are basically modeled into squares, and then a line is drawn through those squares. And that pattern, you will see that pattern being followed by nature as well. And as well as architecture and mathematicians also like that series a lot, and that's also incorporated in various architectural elements, right? So you create an algorithm, you create a logic, a mathematical logic, you feed it, you make it have a physical sense, and you model something based out of the physical capabilities of that mathematical equation. Okay. Now, this is an example that I would like to show what computational design essentially is. What you can see is a diagrid structure. Um, and on the top left corner, you will see a certain logic that has in place, which essentially allows one to vary the diameter, the spacing of the diagrid, and also the curvature. And once it is done, on the right, you can see the model being dynamically varying based on the parameters, and then it can be easily exported to other software because of the capabilities of this computational design software. Okay. Next, now, why parametric design, and why am I going to concentrate on that? So, okay, so if you come from the heavy industrial background, you will see that these structures are basically modeled to support equipment, the mechanical industry, the HVAC industry, the piping industry, and so on, right? So you have very few limitations, you have very few options to give uh, uh, to the interdisciplinary engineer as to what kind of structure that it can support. So that's why generative design doesn't really work very well over there. First, because of the physical limitations imposed by the vendor drawing or the mechanical drawing or whatever it is, piping layout and so on. Also, the loads that a typical structure is subjected to is quite varied. So you have dead load, live load, wind load, seismic load, anchor load, guide load, and so on. And that's why you have multiple load combinations, and trying to fit in for every load combination can be quite laborious in generative design. And algorithm design doesn't really fit the bill as well, right? So, and if you're coming from building industry, so the building envelope is already generated by the architect. So you need to fit your columns in with respect to the location, with respect to the boundary that has been defined by the architect himself. So that's you are left with very few options, and that's why again generative design, algorithmic design doesn't really blend well. Now, parametric design. So, like I said, because of these limitations, that's why you have a predominant display of parametric design in application for structural engineering applications, while also it will be slightly laced with algorithmic design here and there, because it is essentially a subset of computational design and both are slightly overlap here and there. But predominantly you will find parametric design, especially being used by structural engineers. So in this example over here, what you can see is it is a shed, and the shed is modeled along an ellipse, and you can vary the diameter of the ellipse. If I'm correct, the major and the minor diameter both are there. The number of frames, the spacing between the frames, and also the location of shed along the ellipse, right? So that is what you're seeing. So this is a very good example of parametric design, that using by dynamic variables, using dynamic variables, you can actually model, you can actually change this quite easily. Okay, so what is the process of parameterization? So whenever you start with a structure, what I will suggest is you study the structure properly, and at the global level, you determine, hey, what are the variables going to be, and you can, that could be the length, the width, the height of the structure, and so on. And at the elemental level, what are the variables going to be that will help you quickly incorporate changes? That is very vital. Those parameters should be defined in such a way that they're important and then that are susceptible to change. So if the parameters are not susceptible to change, then there's no point in making them dynamic in nature. You can hard code it into the algorithm. But if you have slight inkling that the dimensions of the building are going to change, the thickness of the slab is going to change, the thickness of the core wall is going to change, the profile of the column is going to change, then I'll strongly suggest that you parameterize those variables. Right? How to parameterize them? I'll show that in a short while. So once these variables are determined, you basically make them dynamic in nature, and any change in the value of those parameters will automatically update the model. Okay. Okay, so now in which avenues can you find parameterization? So first is modeling, geometry, modeling, and so on. The second is analysis, and the third is design. So I'll first cover geometry and second analysis. So parameterization of structures, geometry. So say, for example, if you have a very simple steel platform, so what are the parameters that the structure can have that can be basically made dynamic in nature? So the width of the platform, the height, the length of the platform, and then the number of bends. Okay. Now you shift to the elemental level where you say, hey, what kind of bracing do I want? Do I want a chevron bracing? Do I want a V bracing? Do I want an X bracing with an intersection in between, a K bracing, and so on. So you can make them dynamic as well. What should be the spacing of the secondary beam? So let's say, for example, tomorrow, if you have provided, say, 1300 millimeters, but you want to change the spacing to 1100 millimeters, then by making it dynamic in nature, you can actually not only change the spacing of the beams, but you can also actually define the algorithm in such a fashion that the live load on the secondary beams also gets changed because it is tied or coupled with the variable itself. Okay. Then the plan bracing type, the spacing between two bends, and so on. Okay. The last one would be the profiles of braces. So what kind of profiles do you want to assign to the steel, to those beams, columns, bracings, and so on? Now, let's talk about a typical steel warehouse. Would anybody like to take a guess what kind of variables that we are looking at the global level over here? Okay, I'll carry.
Spacing of the bay.
Yes. Yep. That's one of it. Then you have the
Location
length.
of bracings.
Location of bracings, correct. Yep. Then the
Type of
spacing of the
foundation. Type of
height of
foundation.
foundation. Yep. Yep. Correct. Any other guesses?
Spacing
Okay.
of purlins.
Exactly. So the spacing of purlins, spacing of
Girth.
the girth, then the section profiles, then the rafter slope, plan brace type, the vertical brace type already defined, and the location of the doors. Okay. Then this is a kind of a structure that is kind of built here in Australia as well as I think in the States and Canada as well. So what they do is they model the walls. So these are kind of precast walls, but semi-precast in a way that these walls are precast as a slab on the site itself. And then they are tilted and then erected in a upright fashion. And then they are tied to each other with the help of rafters and bracings and tie braces and so on. Okay. So in these kind of structures as well, you define, you can define the global variables and the local variables that are the bracing type, spacing, location of door, cap, and so on. For this is basically an example of of a tabletop foundation. Over here, just like the previous models, you can make the variables dynamic that correspond to column location, penetration location, anchor bolt location, slab thickness, raft thickness, the column dimension. Now, when it comes to analysis, what are the things that we look at? Okay, so the first is you get by extracting the member forces of certain members, you can create a loop and you say, hey, I want to increase the profile size until the bending moment is reduced to this quantity. So that kind of looping arrangement can also optimization also you can do using this kind of philosophy. Okay, so member forces, deflection, reactions, and so on. So on the right, you will see that the steel platform that I showed from the Tekla model. What we have done is we assigned a couple of sections to the columns, and if you can see that black dot over here, so we were continuously importing the deflection value of that dot of that node from SAP2000, and the software was continuously interacting with SAP2000 in a two-way fashion. So changing the section size, performing the analysis, extracting the deflection back into the software, and then putting them, showing the results. And then what happens is you basically put in the solver to the optimization solver to reduce the deflection, and then you determine which section size is suitable for you. Now, the another intelligent way of doing it is once you tie a cross section for the column, you can actually also tie that. You can extract the flange width of the column and say put in an algorithm that controls the beam size based on the width of the flange of the beam itself. So, say for example, if you're providing a moment connection and you want to restrict a beam that is not wider than the column, then you can also incorporate that logic into the algorithm and essentially change both the column size and the beam size if you want to. Although I didn't do that, but that's a possibility. Okay. Then coming down to say, for example, if you have a raft foundation, then you can use a soil pressure. You can use the bending moment generated in the slab in the raft to optimize the thickness of the raft. Okay. Now, on the right hand side, what you're seeing is a mesh sensitivity analysis that we automated. So what we did was we predefined a few mesh sizes, and we recorded for every mesh size the soil pressure. And so you have, so I think we gave around, although we have restricted the video to 3 or 4 over here, but we gave around 15 or 16 such options. So 100, 200, 300, 400, 500. And then you'll start noticing that the soil pressure won't change beyond a certain mesh size. And that is the optimal mesh size that you can actually adopt for your model. So this kind of mesh sensitivity analysis can also be easily automated using the computational design fashion, the parametric design fashion. Okay. You'll see that I didn't have to struggle with providing the cuts or the everything was automated using the plugins available, and we were able to do that quite easily. Okay, now I didn't touch much upon design is because the analysis and geometry essentially defines it. So if you want to, you can do optimization based on profile sizes. You can do optimization based on the reinforcement. So you, although SAP2000 has a very crude way of calculating reinforcement, that's why I don't use it. But you can actually write your own program in a computation design software, which computes based on the bending moment generated, which it computes the reinforcement, and then you can link it to your optimization algorithm, and it will keep on changing the depth for a particular reinforcement size and spacing if you want to. Okay, so now what are the software used for parametric design? So in the whole market, there are essentially two software. One is Autodesk Revit and Dynamo, and people also couple it with a software called Rhino inside Revit. That is nothing but essentially Rhino. I 100% use Rhino and its add-in called Grasshopper to do this entire thing. Rhino is a very neutral software. You can model architectural elements, you can model buildings, you can model ships, boats. People have also modeled surfboards, 3D printed them, and so on. And I basically use it for structural modeling. Okay, now Grasshopper 3D doesn't come separately. It is an add-in of the software, and you need to purchase Rhino 8, which is the latest version, and then what do you say? And Grasshopper comes along with it, and you can start controlling Rhino using Grasshopper. Okay, so what does the UI look like? So on the left-hand side, on the top left, you will see that how Rhino 8 typically looks like. You have 4 windows: perspective, top, front, and right. If you want, you can put in the left view as well. So it is, it is more or less like modeling software only. So not much guesswork, at least for structural engineers. So the 3 types of elements that I use are 1D, 9 elements, 2D, that is plate elements, and 3D, that means volumetric solid elements, right? So so the 2D and 3D are called breps, boundary representations in Rhino language. Yeah, for a structural engineer, the 2D, I prefer to call it as a surface or a plate, whatever it is. And if I'm talking to an architect, what I call them as surfaces. And if I want to differentiate between 2D and 3D, I call the 3D solid elements as a volumetric brep. Okay, so the architect immediately understands, okay, it has a certain volume rather than just occupying a certain plane. And once you go to tools, don't worry, I'll demonstrate all these things as well. You go to tools and you click on Grasshopper. This is the window that opens, and it is called Grasshopper Canvas. Okay. Yes. So once it is done, if you take a look at Grasshopper, then the Grasshopper window on the top looks like this. The menu looks like this, and if you can see my mouse hovering, these are basically plugins. So some of them are native to Grasshopper, and the others are third-party plugins that I've installed. So these plugins help you introduce certain components. So this is basically called a component, which will help you to model different types of elements. And on the left-hand side, what you can see is a slider, and that essentially helps you to parameterize stuff. So on the bottom, what you can see is I have drawn a line using 2 points, and I vary the second point of the line using these lumber sliders. So when I say to make a variable dynamic in nature, that is what I do essentially in Rhino and Grasshopper, that I assign a number slider and I make it dynamic in nature. So if I change the intensity of the number slider, the location of the corresponding element also changes. Okay. Now, these plugins help you establish, most of these plugins help you establish two-way communication. That means you can send information from Rhino and Grasshopper to a software, say Tekla or SAP2000, and then import the results based on the design of the plugin. Obviously, if the plugin has incorporated it, then you can import that information back as well into Grasshopper. That is what I essentially did for the soil pressure and the deflection example that I showed, that it exports and then it imports the results as well. Okay, so now from where can you download these plugins? So the Food for Rhino is a website where you can download most of the plugins that are available for Rhino, and quite a few of them are paid, quite a few of them are free, and so on. But for structural analysis purpose, that means if you want to export it to a particular software like SAP2000 and ETABS, currently there is no arrangement for StatPro. There is a company in India that we are talking to right now, but they are facing some problem in establishing an API connection with the software from Grasshopper for some reason. and the tech team of Bentley is not responding to our request. So, but they're still trying to figure out if they can just export an STD file and then establish at least a one-way communication. But hopefully, let's see. Keeping our fingers crossed. But if you are talking about ETAP, SAP2000, and so on, so there's a company called Geometry Gym based out of Melbourne. So what they do is they give access to those plugins on a subscription basis, yearly subscription basis, and that is what we do as well. We purchase the plugin from them and we use it for our own applications. Okay. So what is the workflow? So we model a structure in Rhino using Grasshopper. You can actually model it manually as well. So one of the demonstrations will actually show how you can manually model in Rhino, almost similar to like StatPro, and then import the workflow, import the elements into Grasshopper, and then use the same workflow of exporting to SAP2000 or Tekla. So you model your structure in Rhino using Grasshopper, and then you export it to Tekla. You can use the same model to export it to here. This software is Space Gas, an Australian software. The stage construction, I do it in SAP2000, so I can use the same model to generate a SAP2000 model as well. You can use this same model to generate your GA drawings as well. And then IdeaStatic has also a decent plugin to export connections as well if they have been modeled parametrically. Okay, so what are the advantages of Rhino and Grasshopper? It's a very neutral modeling platform. You can tweak it as you want to. It connects to various software via plugins. It enables optimization and also makes modeling parametric in nature, which really simplifies and shortens your design time if done properly. If the algorithm is set properly, okay, if the script is set properly. So this method of modeling in Rhino using Grasshopper is called visual scripting. So when somebody says, can you give me a Grasshopper script? What he's asking is for the GH file, .gh file that the Grasshopper file generates, the Grasshopper canvas generates. Now, what are the choke points? So because it is designed for, parametricity, now how many real life structures are actually parametric? That is the struggle that we were having for the last 2-3 years as to how do we use the software to actually reduce the design time rather than doubling or tripling it just in order to make in the theme to make it parametric, because not all structures need to be made parametric to the fullest extent. The dilemma is a structure is truly parametric in a certain sense, and a structure is truly non-parametric in a certain sense. So it depends on your perspective how you look at it. So we were trying to come up with a middle ground where we could actually determine, hey, how do we use this so that it still reduces your design time? You, an engineer, actually generates the Tekla model, which I feel in this day and time should actually be the case, where you generate the concrete or steel Tekla model, and then for what is a non-standard connections and those things, the Tekla modeler takes over. For generating the drawings, the Tekla modeler takes over. But you still have control, and because that really helps your understanding. Because as structural engineers, we are so used to center modeling that we sometimes do not have a good grasp of how the structure actually is in the physical space. And that's why this way of modeling and working helps engineer. So he doesn't have to spend double the time to model it in, say, SAP2000 or StatPro or Space Gas, and then again create the same model manually again in Tekla. You can combine both of them, so that reduces the design time, design cost, and reduces the load on the Tekla modeler as well, so that he can spend more time on actually checking the drawings, fabrication drawings that are generated. The second thing is, so the Grasshopper works from a left to right fashion. So as you start placing components, the more the amount of components, the more that it takes time for it to process. So any change that you do on one component, the entire script runs once again, and there are ways of stopping it, but that's how it traditionally functions. So what is the best way is basically you develop your own plugins to automate the certain modeling process or loading process or analysis process. We generally like to use C# as a language to develop these plugins, because there's a very nice video by a German professor who has proved that C# plugins function 10 times faster than Python plugin. So that's why we stick to any kind of development, hardcore development, we still stick to C# rather than Python. So how did we come across the first choke point as to, how do we take care of modeling the non-symmetric structures? So we have come up with our own plugins that will soon start issuing on a subscription basis from January 2025, using which you can actually quickly scale up a lot of steel and concrete structures relatively easily, rather than using native Grasshopper components. So now coming down to the last topic, which is other applications of parametric design. We did an interesting exercise a couple of months ago where we determined, hey, if we have a crane and if we have a steel and a concrete structure together, and we want to take into account what is the optimal crane location around the structure so that it is able to, from that particular location, it is able to lift and put into place most of the structural elements. So, we automated this algorithm, and as you can see on the left-hand side, it basically picks up from the mesh points. It picks up a particular crane location, and determines which is the most optimal location for the crane to lift and put into place all the elements in one single go without having to change. Right. So I'll just skip to the end. So that's about it. So that is the location that the algorithm has determined that is the most optimal location for the crane to be placed so that it can put lift from its surrounding vicinity and put it onto the actual site location. This is another exercise that we did for a pile cap foundation. So the limiting criteria that we gave were the minimum spacing, the maximum spacing, the edge distance, and the number of piles. So the number of piles were predetermined, and we wanted to know what are the most without taking into consideration the loading, but which satisfy these geometric limitations. What are the possible combinations? And this automation process gave us a set of locations, pile locations for the given number of piles, and we then use them and then export that to our analytical model and use those locations to model our piles and check whether this geometric location criteria is also satisfied along with the loading criteria, whether all the piles are safe or not for all the given load combinations. So I don't remember how many solutions came, but I think it should be more than at least 15 or 20. So that's the end of the presentation over here. So please let me know your questions if you have any before I start with the demo process. So any questions, guys?
I would suggest we can finish the demo, then we can have a half an hour question run.
Okay, sure. Okay. So the first demonstration that I will give is for a steel platform that I showed. Client presentation, Grasshopper, steel platform. So okay. So hope you guys can see all the three windows. See Tekla window, the Rhino window, and the Grasshopper window. Okay, so let me enable that. And there you go. Okay. So now I didn't use the in-house developed plugins. All the variables or the components that have been used our native Grasshopper. No external plugin or no in-house developed plugin has been used over here for modeling purposes. So I'll vary a few variables and show you how dynamic it is. So I'm varying the platform height over here. I'm varying the platform width. The number of frames can also be changed, but I would like to actually demonstrate this over here, 1000, the secondary beam spacing, and how it automatically eliminates the secondary beam that doesn't fit between two primary beams. Okay, and let me just increase the maximum spacing 2000. Fun to demonstrate. Right? Now, the other interesting thing is now this secondary beam spacing is also tied with the live load. So you will see secondary beam spacing and is tied to the platform live load. So I've given it an intensity of 5 kPa. And every time I change the secondary beam spacing, this load also gets automatically updated. And subsequently, your SAP2000 model also gets updated. Okay, so that's the beauty of doing parametric design. Okay, so I'll scale it back to 1000. And now, I hope you are able to see that the Tekla model is also getting updated automatically as I change the dimensions over here. Now, what I will do is I'll quickly go to the structural analysis and design part. So as you can see, anything that starts with GG is basically the Geometry Gym third-party plugin that I've used for exporting the model to SAP2000, loading it, giving it releases, giving it supports and all those things, and then extracting the load information and perform the design as well. So I'll just now bake it to SAP2000. So the process of exporting is also called baking. And if you once you have modeled in Grasshopper, you can see that you cannot, I'll demonstrate you that you cannot select it in Rhino window. It is only for preview purpose. If you want to export it to Rhino and then control manually in Rhino, then you will have to do the process of what is called baking, basically exporting. So now it is exporting all the structural information to SAP2000 and yeah, now I will solve it. Okay. Now using these components, what I've done is extracted the node displacements. So as you can see, the node displacement for a particular node combination has been extracted back into Grasshopper, and then you can use the same result to perform and to put in an optimization loop and then perform the optimization process. Okay, so yeah, so that is a typical workflow. Now let me show you another example. So that has been disabled and control space save. Close this as well. Okay, delete the model. And now I will show you a steel warehouse. So that I'll actually show you how you can do manually. Please bear with me. Steel structural rack. One thing is that once you start using Rhino and Grasshopper, you need to learn to be patient. If it is not responding immediately, don't keep on clicking on the cross button trying to close the software or use Task Manager to forcefully close it. If it is not responding for a brief amount of minutes, then do it. Because there will be a risk that you might be corrupting the script. And once the script is lost, then there's nothing much you can do. There are some expert programmers who go into the backend and try to derive it using XML or something. But if you are not well versed in programming, then I would strongly suggest to be patient with scripts. Especially once you start incorporating Tekla scripts, then it really does get slow. Okay. Now what I will do is I will put in. Okay. So let me just close this. Do you want to say this? No. Okay. Okay. So this is something that I modeled in Rhino natively using point lines and those things. So this is a point. Let me just draw a line over here. So say, for example, if I wanted to draw a brace in this direction. So as simple as that. Yeah? And the beauty of it is that you don't have to break your beams and all those things at intersections. Your structural analysis software should be smart enough to incorporate. SAP2000 does implements physical modeling. So what I mean by that is physical beam modeling. Essentially, what it means is you don't have to break them at intersections. You have to model the actual physical length. And that is very helpful because the same physical length model is then exported to Tekla structures. Okay. And unfortunately, in StatPro and SpaceGas, it is not like this. So we had developed some in-house tools that help you break those beams. You don't have to break it in Rhino if you're doing it manually, but you can break it in Grasshopper and then pass off the same beams to StatPro. But because you have the physical beam model, you can still use it to export to Tekla to create an accurate fabrication file. Now, as you can see that I have drawn the border of the, what do you say, border the raft foundation, model the braces manually, model the secondary beams, model the primary beams, and so on. And then I have kind of imported them into Grasshopper using layers. So I modeled them in different layers and have, what do you say, imported them and assigned them properties. So that's why the moment I open the script, because I had assigned them properties, you can see that you can see a full-fledged 3D model in Rhino as well. Okay. Now, let me do a very interesting thing, especially if there are predominantly STAD users. You'll see that how we have automated meshing, and it is so easy to do meshing. So there you go. So based on the mesh, because we have parameterized the mesh resolution, we can actually control the meshing process relatively easily. And the moment you change the location of these points, I'll have to import it. I will not mess around with it now, but if we change it and rerun it, then the mesh will incorporate that node point as well. A common node will be created at that point, and all the mesh will have contiguous borders at that particular node. Okay, so really eases up the meshing process using third-party meshing tools. Yeah, again, it's not native to Grasshopper. Grasshopper can do meshing, but you'll have to do a lot of process to create contiguous meshes amongst, say, for example, the slab and a wall, a raft and a column node, and so on. So we use certain third-party meshes to do that. And then you can, again, bake the model to SAP2000 and okay. I'll just put in the what is it? Only the self-weight load case over here. You can actually control the orientation of their mesh elements as well. So if you want M11, that is what SAP2000 Lingo is for the local LCS, that means local coordinate system of the plates. So you can actually control up to a certain degree the orientation of the mesh plates, the plate area as well. Okay, so as you can see, this has been generated, and if you want, you can actually import the soil pressure results as well back into. So for all the area elements, the soil pressure has been noted and then imported back into Rhino and Grasshopper. Okay, so yeah, so this is one more demo. Now I'll show you a full-fledged steel warehouse. steel structure with raft has changed. No, okay. I'll show you it's a steel warehouse. Does anybody have Tekla modeling experience or uses it in the firm as well? Who doubles up like an engineer and as a Tekla modeler as well? Oh, not tilt up, my bad, sorry. Okay. Guys, I like my presentation to be interactive, so kindly answer in yes or no, or you can even put it in chat. My query was, is there any engineer who actually uses Tekla structures as well as performs analysis and design?
How about in Revit?
You do it in Revit?
Yes, yes.
Okay. Robot in Revit. Awesome. Okay.
No, not robot. I mean Revit. ETABS to Revit like that. CSI to Revit.
Right. Okay. Then I'll show you something, Rhino, and I'll show you something very interesting. When you model your girts, so the girt is perpendicular to the rafter. So this is your rafter, for example, and this is your, not girt, sorry, purlin. So this is your purlin, right? Now, when you change the slope of the rafter, your purlin again needs to be changed so that it is perpendicular, right? So I'll do that exercise right now and show you how easy it is once you set up a proper algorithm, how easy it is to do. Okay, as you can see that the, right, so the purlins are perpendicular, right? Now what I will do is I'll quickly change the slope of the rafter from 3 degrees to 10 degrees. So I'm changing it to 10 degrees, right? And I just need to make a few changes. And then go back over here and just make my grids again. So this script has been generated using our in-house developed plugins. And that is why it is quite quick to do that. And now, as you can see, the slope of the rafter has changed and the purlin has automatically adjusted. So now it will also update, although I won't demonstrate at this moment of time, but if you had a SAP2000 model or an analytical model attached to it, and it will also quickly update your analytical model as well, along with the loadings. Now, the beauty of that is, if you have used ETABS or SAP, you will know that there's a command called area to frame loading, and we extensively use it to perform wind loading analysis to assign wind loads. And because of this feature, once you have modeled, we have developed some in-house plugins that quickly help us model the plates. That means the areas that determine the extent of the wind loading. And because these are rigid plates, they don't have any bending property. They transfer the entire load onto the surrounding rafters and columns. And any change that you do in the slope, it gets automatically updated. So the plate also moves, and the load also gets updated eventually because of that. Okay. So there you go. So now you can see that the entire warehouse has been updated with a small change in the slope, and that is how you do stuff. Okay. So as you can see that these we use. So anything that starts with TM is an in-house developed plugin. So it is TM column builder, TM primary beam builder. So we have many components for building girds, purlins, and so on. And we have tried to introduce quite a few features in there that you can say, for example, if you want to put the purlins, let me do a very interesting demonstration over here. See, if I want to change, let me just disconnect this and Did you see that? I don't know. Over here, did you see that a new brace has been modeled? A tie has been modeled. So we have configured somewhere around 18 to 20 types of braces, if I remember correctly, which will quickly scale up these types of bracings, and you can immediately change if a bracing pattern doesn't suit you. Okay. So XV brace 2. So and similarly, we are done for plant bracings as well. I'll go to girts and purlins. So as you can see over here, I have provided a custom length list, but you can actually provide girts based on number of girts. So it calculates the space, and then so if you want to, it calculates the spacing based on the number of girts you want, and then assigns generates the line work for the girts in that fashion. If you want to provide, say, I want to provide girts at every 1,000 millimeters, so then it will compute the spacing and then provide girt every 1,000 millimeters. If you want to provide a custom length list, then you can actually use this drop down button to set the custom length list, which you have done over here, and then vary the girt spacing accordingly. Okay. So yeah, so we have quite a few things over here. Then you can also actually move the door. Let me see if I can do it properly or not. Yeah, so as you can see that the connection is also getting updated like that. Connection says the cutoff portion for the GUT in this location. Now, the natural question next is, can you assign connections as well to Tekla from Grasshopper? Yes, you can. It's a fairly laborious process. And you need to provide a few extra details as well sometimes for a few connections, because what happens is when you're modeling a connection in Tekla, based on the plane, location of the plane, the camera, and the mouse, it kind of judges certain parameters by itself and assigns those parameters in the packet. Uh, the local X plus, Y plus, and those things, if you have ever modeled a connection in Tekla. Those things cannot be transferred from Grasshopper to. So sometimes it models the connection in a reverse fashion. So that's why you have to feed those values additionally to the connections. But it still is a fairly good way of assigning typical standard connections using just, I think, the top two logic. I managed to generate nearly about 200 Perlin connections between the rafters and the purlins using just six combination, using just this 6, 1, 2, 3, 4, 5, 6 connection components. And if you want to change, then everything gets you just change the attributes that come with the Tekla connection file, and everything gets updated by this logic. Okay, so this is a steel warehouse. Now I will jump to say no, close. Okay. Now, now I will show you a tilt-up warehouse. Rhino 7. So I'm currently using Rhino 7 because we started off making these components for Rhino 7. We are slowly migrating to Rhino 8 because that is the latest version. The difference is that the components need to be changed to the .NET Core, .NET 8 if I remember correctly, whereas the older Rhino 7 works in .NET Framework. The Rhino 8 also has a compatibility mode where you can use Rhino .NET Framework, but I think it is more robust to redevelop your components, your Grasshopper components to adhere to Rhino .NET Core. Sorry. Okay, so there you go. I will not activate the board peers because it takes quite a while, but I will quickly activate the other elements. There you go. Now, we had developed a native Grasshopper, in-house Grasshopper plugin components to model these panels as well. So you can model the openings, you can model gaps between the two panels, you can model notches. If there is a certain bow that is a manufacturing defect that happened while casting, you can actually model the bow, and once you mesh it, you don't have to give that L by 20 or that certain assumption. The bow itself is modeled into your analytical model, and it will generate the eccentric moments because of the downward loads automatically. The software will generate them automatically. Now you can see that I will parameterize this opening, and based on the location, it is the cutout in the Tekla panel is also getting updated. Okay. So yeah, so that's about it for the panels. What I'd also like to demonstrate is something called a panel lifting analysis. So once these panels are cast on slab, okay, before that, I'll show you how we are working on generating drawings. So once these panels are modeled, you need to generate the GA drawing of the panel, which shows the CG of the panel, the lifting point CG. So you have 4 or 6 lifting points, whatever it is, and you need to find out the center of gravity of those lifting points, and then you have the CG of the panel as well. And I think there's a rule which states that the CG of the lifting point should be above the panel so that it doesn't rotate downward, but it rotates upwards, something like that. So it is if you were to compute 14, 8, 3, 10. Yeah, 14 is all one. Okay.
It's okay. It's okay to ask some question.
Bhushan, I'll leave it to you, Bhushan. Is it all right if they ask the questions now, or you want to keep it to the end?
Yeah, a shorter question answer can happen.
Okay. This geometry modeling from the Grasshopper, it will direct transfer to STAAD. I mean, STAAD will just do the analysis without the geometry modeling was done in Grasshopper, in Rhino.
Okay, so if your question is, what if I model directly in Rhino without using Grasshopper? Can it still export to STAAD? Correct?
No, Rhino or Grasshopper. The geometry modeling, because I'm not much familiar. If what I'm asking is the geometry modeling was it will happen in the Rhino or Grasshopper, and then the analysis will be done in SAP2000.
Yes.
Oh.
Correct.
And then
Yes.
the geometry will transfer to Tekla.
Correct. The
Automatic.
same geometry. Correct. So you don't have to model them twice in two software. You model it on one single platform, that is Rhino, and then the same model. So the biggest roadblock in the previous year of exporting models directly from Tekla to STAAD or STAAD to Tekla was that in STAAD everything was modeled center to center. Whereas in Tekla, it is generally top of steel or top of concrete, right? Now, because of this Grasshopper plugins that has been released by Tekla and by Geometry Gym and so on, you can stick to center modeling in SAP 2000 STAT, and then you use the same model, but you do few changes using the Tekla native plugins that have been provided by Tekla, and it automatically generates a TOS model. So that's why you don't have to do it twice. Okay.
Yeah, that's my second question. That's my follow-up question about the center to center, how it will manage. Okay.
Yeah.
And okay,
yes, it is very simple.
I understood that you're doing in Tekla, but in my case, I will go in Revit. Yeah, your add-ons is prepared in Tekla, but it is possible also in Revit, right?
Although I've not done it personally, but I've seen quite a few videos on LinkedIn and other people's work. They use Rhino inside Revit to do the same process, so it should be possible.
Okay. Thank you.
Okay. So Right. So this is something that we had a sample study that we have done. That once we have a precast panel, so you can see that the CG has been computed automatically by the software. It's a very simple tool. You say area, and then it calculates the CG of the BREP that you have fed, or the surface that you have fed, and then you print it and print it. Windows set. Okay, I'm not setting up anything, but essentially steel platform. Wait, save. Yes, I want to replace it. And there you go. Your panel general arrangement drawing has been generated. So you can, I didn't vary the dimensions. And so a fair bit of cleaning is required. But imagine you have 100 panels, 200 panels, and so on. The drudgery of modeling each panel separately and then linking and then maintaining that mathematical accuracy with your SAP2000 STAT model, and then maintaining the physical accuracy with Tekla. Everything you are controlling through one model source. So you model all the panels in Rhino and Grasshopper, you link it and generate these drawings. You link it to SAP2000 and you link it to Tekla structures as well. Okay. The second last one that I wanted to show you was a panel lifting exercise that we did. I'll just show you that Grasshopper panel lifting analysis, and there you go. So, by the way, the drawing tool that I showed was developed in Rhino 8. The script was developed in Rhino 8, and you must have seen the jumbled up spaghetti. That's what they call too many components, too many wires. So that is what happens when you use native Grasshopper components. That is why we strongly suggest to use or develop your own in-house plugins if you know programming, or purchase these plugins from somebody else that will help you smoothen this process. So that was a case study that we did. Now what we'll do is, because now we have understood the process, we'll develop a C# plugin to automate the entire process. Okay, so I hope you guys can see the panel. Now I'll just see how easy it is. So this is a plugin that we generated in-house to perform the rotation process and move the lifting points and so on. So as you can see that I can quickly change the orientation of the panel. I can also move the number slider to control the lifting points. You can see that this lifting point is getting affected because of it, and that's why the lifting point CG is also getting it's the geometric center. Sorry, I've been using CG, but basically what I mean is geometric center of the lifting points is also getting updated automatically. And then once you've done that, once you're very sure you're given assigned all the load cases and combinations, you just press bake, and it exports it to SAP2000. And currently I've given it only self-weight load case, but what you can assign, there's a suction pressure and other load combinations as well. You can create it and assign it. Okay, so once you press solve, it solves it. Display object load assigns. No, let's do deform shape. Deform shape, draw contours, resultant, so on. So there is a deflection. And yeah, it gives you a fairly good estimate of what to say, fairly good estimate of what will be the deflections and the stresses in the panel and the bending moments as well if you want. Okay. The other beautiful thing is that, say for example, if I'm using space gas, because predominantly most of the people use space gas over here in Australia. But space gas does not have staged construction analysis, but SAP2000. So I use the same script to generate models in both the software, with an additional few commands to generate the stage construction load case. and export it to SAP2000 and perform the sales constraint analysis over there in that software and perform the normal analysis and design in space gas. So you will be looking at saving a lot of time because of this philosophy. Right. So this is the one. And is there anyone who does dynamic analysis of block foundations or anything like that?
Yeah, I have experience in that.
Yeah, experience in it. Okay. So what we have adopted is we basically generate the stick model, what we call the columns are 1D elements, and the raft and slabs are 2D elements for static analysis, and then we create a solid model to perform the dynamic analysis and capture the amplitude. Okay. Now the problem is if there is a change in the dimension of the opening or something, then you have to update both your models and your mesh goes haywire, and you have to redo the meshing process and so on. So I'll show you something interesting that we have developed. Okay. So ttf.gh. Let me just find that. Okay. Let me just first open the only the model and see if I can demonstrate to you the parametric way of doing things. Okay. So this is your stick model. This is your solid model. And let me see. I can change. Can you see the raft dimension changing? So yeah, because it has solid elements and those are meshed, it gets painstakingly slow. So that's why you might not be able to see it immediately. But if I switch this off and if I go back, 9310. So there you go. Your raft has changed. Let me see if I can 9150. Can you see the opening changing? The location of opening changing. So you can actually also tie the location of anchor bolts with respect to the location of opening using algorithmic logic. And then as the, I didn't do that over here, but as your opening shifts, say for example, if you wanted to provide your anchor bolts at 250 millimeter at certain locations from the offset of the opening, offsetted from the opening, then you can tie your logic in such a way that as your opening moves in a particular direction, your anchor bolt locations will also move along. So that's how easy it is. Now I will open the actual model, which communicates with SAP2000. So what I mean to say is over here, the 1D model is tied to the solid model. So any change that you do to the 1D and to the stick model, the location of opening and so on, it gets automatically the dimensions of the column. The solid model also gets updated automatically. Solid measures are difficult to incorporate, so that's why we created an in-house component to manually divide the solid elements. Okay. Oh God, why did it give an error? Okay, let's see. Apologies beforehand if I'm not able to demonstrate this, but it was working all right when I last checked. Okay, so there you go. Let me switch on the meshed and yeah, so that is your meshed this model, and this is a solid model. Let me just click on bake. It should open SAP2000 and it will take a while because there are approximately 2000 solid elements, if I remember correctly from last time. So it takes a fair amount of time. So if you have any questions, please let me know. So here the model has been generated because SAP2000 has ready availability of rigid links. So that's what I've used to model it. Now I just press solve and okay, that's solved. Now let me display the amplitude, show plot functions, and so that's your transient and that's your steady state displacement, if I remember correctly. So, and these results can be imported back into Grasshopper as well. I think I have done that. So yeah, so that is the amplitude in the XYZ direction. Okay. So yes, so that's about it from my end, folks. Now questions, please.
Now, coming to this performance-based design, now currently there are some of the codes getting revised based on this. So they are fixing some performance requirements such as some displacement or drift or some other force limitations and all. That how can we control using this software so that we can automate that? Because if we are getting
Right.
some displacement of 100 mm, the limitation may be 10 mm. How can we do it in a faster way using these softwares?
Right. So you remember the video that I showed you during the presentation? Let me just bring it back. Right. So say for example, what you start with the process of modeling your structure in Rhino and Grasshopper, right? I'm guessing that, or I'm assuming that you must be using ETABS to perform performance-based design, right? Or Perform 3D. Now, I don't know whether Perform 3D has API access and they have third-party plugins that help to export to Perform 3D, but you definitely have geometry engine plugins that export to ETABS. So what you do is you set up your model in that fashion, and then you put in an algorithmic logic that basically imports the deflection or the drift, whatever it is, for a particular level or a node back into Grasshopper. Once you have done that, you put in the, an optimization routine which states that if this number, you normalize that deflection. So say, for example, if you want the permissible as 10, and the actual deflection that you're getting is 100, so 100 by 10, that is the ratio that you use. Okay, so the numerator becomes a variable that comes from ETABS into Grasshopper, and the denominator is the actual limiting value. And you tell the optimization like Galapagos or there are multiple optimization algorithms available, plugin components available, and you say try to minimize this and make it less than 1. So it keeps on, and then you say by varying what? So by varying over here, like I use the column sizes. So you can use the thickness of the core wall, the dimensions of the column in that particular direction of the drift, and you put them as, and you can actually do multi-variable optimization as well. That means you can actually control the thickness of the core wall and the thickness of the columns if both are contributing to the lateral deflection. And you can actually, what do you say, you can optimization, you can put in an iteration procedure in place, which doesn't stop until you meet it, or it doesn't meet it. The solution doesn't converge because the profiles or the section sizes do not adhere to certain logic that you have incorporated in, and will simply stop and say this maximum that the deflection can be controlled is up to 50 millimeter for the given profile sizes. So you say, okay, let's increase the profile sizes at the thickness. Instead of 200, I give it 300 now. Increase the column sizes from 1000 by 1000 to 1200 by 1400. And then you watch the deflection going down as per your expectations. Does this answer your question?
It's fine, but instead of giving some other thing manually, just if we give the limiting deflection only, will you not able to do everything automatically without any intervention of the structural energy? Just if you give the limiting deflection, can it do automatically all the things?
Yes, that's what it does. It does everything automatically. So once you set the, you'll have to generate the algorithm. You'll have to model, you'll have to do the scripting by yourself for that. Once the scripting is done, then it can be automated, not by just, well, you can write your own C# or Python plugin that talks to ETABS API. And what you can do is you can check the current instance of ETABS model that is open. You absorb the deflection. You can do it via Excel as well. You don't need Rhino or Grasshopper for that. You can do it via Excel as well. And you link certain section sizes to certain inputs in Excel, and then you automate in that fashion. So say, for example, if you have the ETABS model already modeled, so that is the approach that you can take, that you just link it to certain variables. You can do it via Grasshopper, you can do it via Excel, anything, and then you can automate it. But just by like everything to be done by Grasshopper, that can't be. You need to model and set up. You can there are also certain arrangements where you can also import an existing model from ETABS back into Grasshopper and then reverse engineer the logic. And that partly reduces your work if you've already modeled the structure manually in ETABS.
Okay, thank you.
Okay. Yeah. Any other query?
Yes, sir.
I have a question.
Sorry.
Next question, we have a group video, a group photograph. So all can on their camera. I'll just click a snap.
Yeah.
So all can on their camera for a minute. Okay, a few more are there. All can on the camera. Sharad, Shankar, Kirti, Akib.
You're feeling shy on the weekend, huh?
I mean, maybe they would find a place before on the camera. So I'm just taking the picture now. Yeah. So please smile. Yeah, thank you. We can continue with the question answer. What I have understood, parameter design. Okay, design is based on the parameters that we set for the control of the structure. Now the parameter can be the modeling, parameter can be analysis, parameter can be design, or parameter can be the checks. So we can do the coding for that particular phase for what we want. Okay, and then tune the that plugin with the software so that we don't have to do iterations. The software will do the iteration. So our outcome will be as good as we have understood the problem and scripted it.
Correct. So a lot of times what we do is the moment we get an architectural drawing or a vendor drawing, we immediately start modeling without thinking much about, hey, what if this model changes tomorrow or day after tomorrow? How are we going to tackle those changes? Because it's a fairly manual process, and so we don't give much thought process. We don't assign much thought process to it, and that leads to delays.
First is the concept, then comes the schematic, and then comes the detailed design. So
Detail.
phase wise everything. And if we set the parameter in the initial stage, we can regulate it and save the time for the number of iterations that we have.
Correct. Yes. So what I generally recommend is, if as soon as you get an architectural drawing or a vendor drawing or even a piping layout or something, sit down with a piece of paper, draw grid lines, understand the location of columns, beams, and so on, and then parameterize those based on the grid locations and these things, and then slowly build from there. Obviously, you cannot you cannot achieve 100% parameterization of a model. You cannot identify all the variables in one setting and go. So, but you make it fairly expandable and adjustable, or even collapsible if you don't require certain parameters in the backend. It takes a while. It takes a while. See, it took me at least 2 years to understand what Grasshopper is, and I would say even I have just scraped top 15 or 20% of the software, because it has so many tools, it has so many third-party plugins, and then it is totally geared for symmetric parameterization of structures. So the structures are very uniform in Cartesian systems, or or spherical, cylindrical, and those kind of things. So even I struggled. Eventually, what happens is the client expects, he doesn't really understand all these things, and he doesn't give two hoots about these technologies. What he wants is, am I going to end up saving money or not? So what we had to prove was, this process leads to saving of money at the end of the time, and saving of time, and because of that, indirectly money. So then we went back to the drawing board and we came up with all these in-house developed plugins that help us to quickly scale up these structures and then change and tweak the structure as and we want to. So it took us almost a year and a half to develop these plugins. It is still under process. It will take a couple of months more for it to attain maturity, and we'll release them on a subscription basis sometime early in January. So I think probably the next question would be, where do you want to start learning Grasshopper? So there is a website called learngrasshopper.com, which is run by Christoph. That is a good starting point. But again, I said the examples are fairly very uniform, simple, isolated in fashion. We are going to launch an academy called Tectum Mechanics Academy next year around the same time, in January sometime. But it will be like, if you have access to those plugins, if you purchase those plugins, then you get access to those video lectures as well, which help you model these type of structures. We will also try to release a few videos where you can actually use native Grasshopper components to model structures, but those will be relatively simple and uniform, because that's the limitation of the software. But also the strength is that if you know programming, then you can actually develop these plugins by yourself, or if you are working for a company, then you convince them, and they get convinced that this really leads to time saving, then they can purchase these plugins, third-party plugins.
Yeah, so basically, it starts from understanding the tools that we are going to use. So structure remains the, uh, let's say, the core background. And based on the core background, we have to develop the tools and resources so that they benefit us in time and cost optimization. And this multi-software modeling is also not there now. So first you model in STAD, SAP, or this ETABS or Abacus, and then you have to model it in like detailing softwares like Tekla or Revit. So integration with the softwares become very easy, very fast, that I could see. If your system is supporting that, let's say we have not seen yet for the tall building. Let's say if it is a 40-story or 50-story building, how much time will it take to generate the model from Grasshopper to ETABS, let's say.
Correct.
So
Correct.
that one part is based on that we can decide that how many applications we have, in how much time, and how benefit we get in design changes that will happen in that model. Because 50-story model, there may be many changes that will happen from basement to top. All those things are there, and if this is able to optimize it, then certainly it is an add-on skill. Uh, but it's uh, means applications understanding starts with the understanding of that tool. So basically, first you need to know Grasshopper, Rhino, its plugins available in Tekla or ETABS, and with small example like a portal frame, we can start. That is the first thing we should do after hearing your session and the beautiful presentation that you had made. So this basically shows the application structural engineers can develop in themselves and have a add-on to their skill set and reduce the time for efficiency.
Yes, yeah, absolutely. See, if you my suggestion would be, if you don't know Grasshopper and Rhino at all, what you can do is you can start understand you have a 3-month trial period for Rhino to download it and start manually modeling beam, column, or slab systems in Rhino, like I showed you. Select a point, draw lines, and then you just import them back into Grasshopper. That's a fairly simplistic process. You can find tutorials on YouTube anywhere. If time permits, then sometime next year I can conduct a couple of workshops as well for that. But that might be an ideal starting point if you don't understand Grasshopper at all, especially visual scripting and parametric modeling. That you manually model in Rhino, you import it into Grasshopper, then you use geometry gym tools or any other. If you can write your own plugins to export to ETABS. My understanding is that, my observation is that it is still a versatile software for even for tall buildings. It starts really getting very slow and exhibits lag once you connect it to Tekla using the Tekla Grasshopper Live link. So keep it disabled. It is still very fluid. You can rotate, pan the model, even for a tall building, 100, 150, you might be able to do it easily. Control the model natively in Grasshopper and Rhino. Where it starts showing limitations is that when you start importing, when you start meshing your model extensively in Rhino itself. So in ETABS, you do not have the problem of meshing. You just model object-wise and you export those objects to ETABS. And it fairly does a good job of meshing it by itself. And at least it basically, where the meshing is not contiguous, it will introduce, what do you say, I forgot the name. But basically, there is a feature in ETABS, even if the mesh is not contiguous, it still performs well if you introduce that feature. I forgot the feature's name. But SAP 2000 automation is really poor. So I generally prefer to auto mesh my model or mesh my model in, what do you say, in Rhino and Grasshopper, and then just export the meshed model to SAP 2000. If it is a fairly complicated model, especially non-planar types of, you have a steel hopper or a circular sphere or an intake model or a chimney, those kind of things, I'll prefer to mesh it in Rhino and Grasshopper using third-party plugins and then export the mesh directly to SAP 2000. So yeah, so my suggestion would be to at least start understanding modeling in Rhino, request Geometry Gym for a trial license for 30 days. I think he generally gives it for 30 days first. And then start exporting stuff to ETABS to get a good understanding and use the same line work to create your Tekla. Now, why I strongly suggest engineers now to understand Tekla or Revit, whatever modeling software that is used in-house in your company, is that the clear physical space limitations that can be clearly visualized in Tekla can be difficult to envisage in a center-to-center model. That means, where does the column cut off? Where is the slab bottom? Where is the slab top? How is a slab top interacting with the beam? Are there any beam offsets? If it comes to steel beams and this thing, the end-to-end offset, what kind of impact does it have as compared to a center-to-center model? once you assign a connection. So these things are better understood by engineers rather than modelers, providing edge distances. Now, we have a particular documentation by Australian Steel Institute where they have given the dimensions of of the the gun that helps you tighten the bolts. I forgot the name of the equipment, but basically it's a gun and it has a shaft and you put it on the bolt and then it rotates it at a particular RPM and you can pre-tension it as well if you want to. Now they have clearly defined what is a clear space that you require for the equipment to get in and tighten the bolt. So if you have not provided enough space and if the modeler doesn't understand the implications of doing that, it falls upon the engineer to take a look into it. And if the focus of assigning connections, at least the standard connections, typical connections or unique connections are difficult to model in Tekla without having a good understanding of how Tekla structure works, the work planes and all that stuff. But at least I recommend the standard connections can be implemented quite easily. And those things I generally suggest that workload should shift to engineers and they should be compensated accordingly for that because they help in reducing the design time and cost. I can't hear you, sorry. Hold on. For some reason on the settings. You're on mute, Bhushan.
Yeah, I think Reynard had a question before we were taking this screenshot.
Okay.
Yes, about preparation of calculation. It's possible this Rhino to automate, like connecting with MathCAD, Excel.
Right. So anything that has API capabilities, application programming interface capabilities. So any software that allows a backdoor entry to control the software, you can link it with Grasshopper, ideally. So you can connect it to Excel. There are third-party plugins, free plugins actually. You can export to Excel as well from Grasshopper. MathCAD, I'm not sure if it has an API functionality and whether you can control it via Grasshopper. You'll have to check it. I have not seen till date anybody posting any data on that. But people have done with what do you say, even MATLAB using certain Python functions as well to perform finite element analysis using OpenCs and so on. Yeah, so any software that has API functionality, you should be able to ideally control via Grasshopper, provided you know programming to access that API and use the DLL file to call particular functions or subroutines. Does it answer your question?
Yeah. Thank you.
Welcome. So guys, any other question?
Any particular programming skills are like that you are telling Python, MATLAB or MathCAD, especially which will be useful for civil structural engineering? What is the best programming technique so that we can do all these things?
Right. Okay. So sorry, continue.
Yeah, that's all.
That's all? Okay. So if you do not have any programming experience, I will suggest Excel VBA. I am planning to conduct a workshop. It will be a paid workshop. I'll suggest you to, or like even if you don't want to attend this workshop, it's completely fine if you want to learn from YouTube. But I'll strongly suggest structural engineers to start with VBA if you do not have any idea about programming, because first you have a ready UI that is the Excel spreadsheet available to perform operations, and it is easy to understand, and you have a lot of tutorials available for Excel VBA. Then if you want to alter with bare minimum code, then Python is a language to go to because it has a lot of functionalities available, libraries available that take a lot of time to do natively in C#. So say, for example, if you have an ETABS file and you want to classify the columns based on the 1.2 dead load plus 1.5 live load combination, and you want to group certain columns, Using Python and using eTab's API, you can actually quickly do it, and you can create a chart in Python as well to show those groupings with a particular color, almost with a few lines of code, a couple of hundred lines of code, and the entire process is done. Whereas if you were to do it using C Sharp, it will take, because those libraries, um, um, at least I do not have much idea because I haven't been doing that lately for the last 2 or 3 years. But I don't know if they have developed those libraries now for C Sharp. But from what I remember, it was not so simple to do that. But I've seen people doing it very easily in Python, and they now use Chat GPT as well in combination with Python and eTab's API to quickly do this process. So my suggestion is Excel VBA. If you want to learn hardcore programming, then go to C Sharp. If you want to learn the application side of programming to help you with your everyday process, then Python. And then if you want to switch over to hardcore programming, develop Tekla OpenAPI applications, eTabs applications, or Grasshopper plugins, then C Sharp. Does that answer your question?
Yeah, thank you, sir. Okay.
Okay.
Okay, so any other question? I think you have brief. Yeah.
Okay. What I will do is I'll just share a Tectum mechanics. So we will be keeping you updated. We are creating a newsletter on our Tectum Mechanics website. I'll just share the link with you here in the chat. Please hold on. Please ignore the text. It is still being drafted. Okay, so for some reason, I'm not able to access the chat. Bhushan, maybe I'll send it to you on LinkedIn and you can send it to all of them.
Yeah. I can also email. So all are in the email loop. So we can share the email to all. And also from that, I can update the LinkedIn as well.
Right. Recording minute. This. Okay, so let me just reply all.
So yeah, overall for today, 40 registered participants, all are not able to attend it live. So that way we can share with them all the link.
Oh yeah, sure, definitely. So I'm sending you the URL of the website where you can register your interest. And we will keep on updating you about the in-house plugins that we're developing, and eventually when it is launched, then we'll send a notification as well. And if you're interested and if you want to proceed ahead, then you can get in touch with us.
Yeah, okay. So there were a few participants who wanted to have a course on this, a short-term course of let's say 2-3 months, or how
Right.
many, let's say 30 hours minimum, that way 30-40 hours. So you can also update on that, if there is a course uh, at your end, or we can arrange it. And they had that interest. They wanted to have the course, one course on this.
One course on this. Yeah, sure. Yeah. See, like I said, we are already planning something for that. I'll keep you updated.
Yes. Okay.
Okay.
So I
Thanks a
think
lot, everyone.
very briefly explained all the
Thank you very much.
on the of parametric design, computational design, and I heartily thank you for spending your valuable time in delivering this session, and hope we can have more sessions on this subject as per the interest of the participants. And I also wish you best of luck for these applications that you have developed. And the more it is used, more the people will understand the benefit after that. So I think display it, then it can have more effect on its applications. So thank you all for joining, and thank you, Mr. Prasad. It was a very nice session.
Pleasure. My pleasure. Take care, everyone. Bye.
Thank you. Thank you. Bye.
You.
Thank you.
Thank you. Bye.